So welcome to the first MathSoc talk of this year. And the first person that's going to give this talk is Dr. Ben Barber, who is a fellow at the University of Manchester. So with no further ado, here's Ben.
Thank you. All right, so I want to start today by talking to you about a game. And I don't want to use the name of the game because Hasbro have some really, really good lawyers, but you definitely know the game. It's the one where you have to guess which person your opponent is thinking of out of a grid of people. Okay, so to give an example of this game, I'm going to need a grid of faces, but luckily we're all quite used to grids of faces now because we're constantly seeing them on Zoom. So here's a grid of famous faces from Zoom. This is a cabinet meeting in April, early in lockdown. So I cut out the faces. We've now got 16 people here, and we're going to play the version of this where you are thinking of a person and I have to guess who it is you're thinking of by asking yes and no questions. So, for example, my first question might be, is your person a white man who went to Oxford? And if you said yes, then that cuts it down a little bit, but not a lot. Whereas my second question could be something like, does your person look like they raided the dressing up box and then got into the Zoom call by breaking into their parents' office? And again, if you said yes, I now know that you were thinking of Boris Johnson. So there it took me 2 questions to find out who you were thinking of. And what I want to think about is, was that lucky? Did I play that game well? How should I play that game if I want to find out who you're thinking of as quickly as possible? So let's think about that. If I ask you one yes and no question, there are 2 ways you could answer that. You could say yes or you could say no. But there are 16 different people that I'm trying to identify. So it has to be the case that there could be different people you were thinking of where your answers would be the same. So I can't guarantee to work out which of the 16 people you're thinking of if I only ask one yes or no question. I sort of haven't got enough answers from you. If I ask a second question, now there are 4 ways you might have answered. You could have said yes, then yes, yes, then no, no, then yes, no, then no. 4 is still less than 16, so there could be different people you're thinking of where the answers to your questions would be the same. So I can't be certain that I'm going to work out who you're thinking about. If you go up to 3 questions, now there are 8 ways you could give yes and no answers. Again, 8 is still less than 16, not enough information for me to work out who you're thinking of. If I go up to 4 yes and no questions, there are now 16 ways you could have answered them, and there are 16 people. So maybe I asked enough questions to work out who you're thinking of. And actually, it turns out that I did. I can work out who you're thinking of just using 4 yes and no questions if I ask the right questions. So the way that's going to work is, okay, I want to spare you looking at our cabinet again. So I'm going to get rid of the faces and we're just going to have numbers from 1 to 16 on our cards. So I could, for my first question, I'm going to ask, is the number now you're thinking of a number rather than a person, is it bigger than 8? That's yes or no. You might say, no, it's not bigger than 8. So I now know that your number is between 1 and 8. My next question might be, is your number bigger than 4? And it is or it isn't. Maybe you say, yes, it is. So now I know it's somewhere between 5 and 8. I could then think, is your number bigger than 6? Maybe you say, yes, it is. So after 3 questions, I'm down to it being 7 or 8. And now for the next question, it sort of doesn't matter what I ask. Maybe I say, is your number 7? And you say, actually, yes, my number is 7. So there I asked 4 yes and no questions, and I could work out who you were thinking of, well, which number you were thinking of. And it didn't matter which number you're thinking of. I can always do something that goes a bit like that. And it also doesn't particularly matter what questions I ask. The only important thing is that I get the number of possibilities to cut down by a half at each stage. If I always do that, then starting with the 16 possibilities and cutting down by half every time, I'll always find out which number you're thinking of after 4 questions. So again, the reason that worked is that it's sort of this fact here, right? So if I have 3 questions, there are 8, so 2 cubed ways of you could answer them, but that wasn't enough. Whereas 2 to the 4 possible outcomes is maybe enough, and actually there's a strategy that shows that it is enough. And we can do a similar thing if there are a different number of things. The only important fact is that 2 to the power the number of questions I ask is at least however many things we're choosing from. So if we were doing numbers 1 to 20, I guess I'd need, so 2 to the 4 isn't enough, that's less than 20, but 2 to the 5 would be enough because 32 is bigger than 20. And another way of writing this is that the number of questions that I have to ask, the number of yes and no questions, is at least the logarithm to base 2 of the number of things you might be thinking of. Okay, so that's the key fact about this guessing game. The number of questions I have to ask is always the logarithm of the number of things, as long as I ask the right questions. I can ask the wrong questions. Hopefully I'm not going to do that. Okay, so that's sort of completely sorted out these guessing games. So we're now going to look at something slightly different, which is guess 2. So guess 2 is very like the previous game, except now you're not thinking of one number, you're thinking of 2 numbers. So we've got the grid of 16 cards again, and you were thinking of some pair of numbers, and I have to ask yes and no questions to work out who it is, which numbers you're thinking about. And this could be the start of, maybe this is the start of a whole series of problems, and we'll have lots of interesting things we can think about, try and work out how we can adapt the strategy we had in the previous case to work out what's going on in the more complicated situation where you're picking 2 numbers instead of 1 number. And sometimes maths is like that, but sometimes maths is about hitting things with great big sledgehammers. Because we've just said we really pretty much understand the guessing game. Whenever I'm trying to guess something you're thinking of, all that matters is how many things you might be thinking of. And I'm pretty agnostic about what the things actually are. So before, the things were just the numbers you might have picked, but I could just as well think of the things that you are picking as the things I have to work out which one you chose. The things could just be ways to pick 2 cards, right? That's what I have to discover. I have to discover which 2 cards you picked. So all that really matters is how many ways there are to pick 2 cards out of 16. And well, that's 16 choose 2, which is 16 times 15, ways to pick the first card, then ways to pick the second card, divided by 2, because we don't mind which order we pick them in. So that's 120. There are 120 ways to pick 2 cards. 120 is between 2 to the 6 and 2 to the 7. So I only have to ask you 7 yes or no questions to work out which numbers you were thinking of. Now, the question you should ask at this point is, okay, so 7 questions, but what questions are you going to ask, right? And to be honest, I'm a little bit embarrassed about this. It works, but it's embarrassing. I'm going to write down the list of all 120 pairs you might have picked. And my questions are going to be things like, is your pair of numbers in the first half of the list or the second half of the list? And then if you tell me it's in the first half of the list, I'll ask questions like, is it in the first quarter of the list or the second quarter of the list? These are yes and no questions. So within the rules as I describe them, they're allowed, but it does seem like they're pretty stupid questions. And if that was your opinion, I couldn't say you're wrong, right? They are stupid questions. So maybe we'd like to do something about that later. Okay. So that's guess 2. We've ground all the fun out of that game by hitting it with a giant sledgehammer. So now let's do something completely different. Well, I have just won the lottery. Did I match 3 balls winning £30, 4 balls winning £140, 5 balls winning £1,750, or all 6 balls winning the jackpot? And well, you know, this is what we've seen before. It's the same guessing game. 4 things you've got to work out which the real possibility was. So if you want to know which lottery prize I won, you're going to have to ask me 2 yes or no questions. Nothing we can do about it, except you've got a pretty good idea what the answers to those questions are going to be in advance. Because I probably didn't win the jackpot, and I probably didn't match 5 balls on the lottery, and maybe I matched 4, but by far the most likely thing is I got the smallest prize, just matching 3 balls, winning 30 quid. So it's technically true that if you want to be absolutely sure which prize I won, you have to ask me 2 yes or no questions, but you've got a pretty good idea what the answers to those questions are going to be before you even ask them. So it also seems unfair to apply the same rule to this situation. Okay. Some guessing games. So the next thing I want to say a bit about is image compression. So image compression, first of all, this is about images. You're familiar with images. Here's a beautiful picture of our university. This is a real Hinge bio photo picture, I think, actually. This is an amazing angle. I don't think the university has ever looked this good in real life. I'm not sure I've seen that many trees in my life, never mind in Manchester. But apparently, from the right angle, this is what our university looks like. But what is an image to a computer? Well, it's a grid of dots, of pixels. In this case, there's 512 by 1,280 pixels, and each pixel has 3 bits of color information associated with it. There's like a how red it is, how green it is, and how blue it is. And each of those amounts is a number between 0 and 255. So it's one byte of information, one of the smallest numbers that computers normally store. So that's how much information is in this image, how much color information there is there. But what else is an image to a computer? Well, there's a file on my hard drive somewhere that is this image. And how big is that file? Well, it's 178 kilobytes. A kilobyte is 1,000 bytes. 178 is about 200. So that's about 2 times 10 to the 5 bytes. So somehow we've stored 2 times 10 to the 6 bytes of color information into 2 times 10 to the 5 bytes of disk space. And that's made me slightly worrying, because what that means is, if we can always do that, there have to be pictures, different pictures, that compress to the same thing. In the same thing that if I didn't ask enough questions, there would have to be different people you could be thinking of, where you would answer the questions the same way. The same thing has to happen here. Maybe we're hoping that doesn't matter. Maybe pictures that are compressed to the same thing are so similar that we don't mind. Well, that might be true. So a few years back, a group of researchers did some machine learning to try and recover the original images from highly compressed versions. So here's a very compressed, very pixelated image of somebody very famous. I invite you to imagine who you think this this photograph might be, who this might be a photograph of. So they took lots of faces, lots of photographs of human faces, blurred them, ran everything through a big machine learning algorithm, and wondered, okay, now can we work out what the original faces look like if we give them a blurred version? So I've given you some time now to think who this might be a photograph of, and I'll show you what the machine learning algorithm returned the answer as. They thought it was probably this guy. So what has happened here is the algorithm has done a racism, and turned Barack Obama into a generic white guy. It was fairly even-handed, this algorithm, though. It was also racist towards other people, so this is what it did to Samuel L. Jackson. And to be fair, it also did rather scary things to other presidents. For a while, this was up on the internet. You could just submit pictures to it. So, of course, people submitted pictures to it that were not of human faces. So here we have what the algorithm thinks Wojak, a Minecraft character, Mario, and Link would all look like as real humans. The only one of those that does not give me nightmares is Link, I think. Did a pretty good job with Link. That's a plausible Link. So, yeah, I'm going to move on from that, just literally because I find it disturbing. So there might be images that compress to the same thing. Maybe that doesn't matter. Maybe it does. I don't know. What's the other reason we can actually compress images at all? Well, it's something that you're probably intuitively familiar with, which is that if I start describing this image, starting from the top left corner, my description is going to be something like blue dot, blue dot, blue dot, blue dot, blue dot. And you very quickly get the idea that probably what we're seeing here is a piece of sky. And it's therefore likely to continue being blue dot, blue dot, blue dot, blue dot. So whilst technically we do have to ask, the computer does have to ask what color the next pixel has to be, it's got a pretty good idea in advance what the answer is going to be. So we're in a similar situation to the guess what prize I won on the lottery game, where there's a certain amount of information that has to be transmitted, but you've got a pretty good idea in advance of what the answers to any question you might ask are going to be. So we'd like to do something a little bit more efficient than just ask all the questions that we already know the answers to. And to do that, it's helpful to have a measure of how many questions we sort of ought to have to be asking. And what we're doing here is we're reaching towards an idea called entropy. So entropy is a property of random variables, really. So it could be like a random number you pick between 1 and 16. It could be what color the top left corner of a random image from some collection of images is. So it's a property of some random process, and it's a way of giving a number to how random that process is. And there are various other ways, various other informal descriptions you can give. So one is that it's sort of the amount of information that's in a random variable. It's what you learn by sort of being told the result of say a dice roll, rather than just being told that someone's about to roll a dice. And another way to think about it is it's the average number of yes and no questions you have to ask somebody to learn about the value of a random variable, to learn the outcome of an experiment. Now, so it's a way of assigning numerical values to these things. Things with a high entropy are interesting or surprising, and things with a low entropy are boring and predictable. Okay, so I'm going to define entropy for you in a moment. The symbol we use for entropy is H. So if we have a random variable X, so maybe X is the result of rolling a 6-sided dice. The way we write down, we call the entropy H of X, and we're not entirely sure why that happened, but historians think it might have been something like this. Okay, so I promised you the definition of entropy. It's here, it's scary. Don't be scared, because I'm going to walk us through it It's the first reason not to be scared. And the second is we're only actually going to look at this in two very special cases. So what's going on here? We have some random variable x, and it takes n different values, and these values are taken with probabilities p1 up to pn. So, for example, if x is rolling a six-sided die, then n is 6, and p1, p2, p3, p4, p5, p6 are all a sixth. If x was what prize did I win on the lottery, then maybe P1 is very close to 1 because I probably won the smallest prize, and then P4 for the probability of winning the jackpot is very small. So that's x, and we're given its probabilities. Then the entropy of x, this measure of how much information is in x, is the sum from I is 1 to n of these probabilities pi multiplied by the logarithm of 1 over pi. So the logarithm to base 2 of 1 over pi. And that looks weird. That's a weird looking expression. So if we break it down very slightly, what we've got here is a first part, which is a sum, and then some probabilities. So a sum over some probabilities times something, that looks like we're taking an average. So the entropy is an average of something. What's it an average of? Well, that's the second bit, the logarithm of 1 over the probability. And the way we think of that is that's sort of how surprising seeing a outcome is. So if pi is large, it's close to 1, then this logarithm is close to 0, right? So we're not very surprised if something happens that was actually very likely to happen. Whereas if pi is very small, then 1 over pi is very big. The logarithm of 1 over pi is also big. So rare events, ones that happen with small probability, are very surprising. And then the entropy of a random variable, of a random experiment, is the average amount of surprise we expect to feel after we see an outcome. Okay, so that's the formula for entropy. I said we're only going to look at this in two special cases. The first case is when all of the probabilities are the same. So we've just got a uniform random variable. So this is like rolling a dice, flipping a fair coin. If you picked a number from 1 to 16 at random at the beginning, that would also be an example of uniform random variable. And in this case, and this case is nice because loads and loads of stuff cancels. You get all the probabilities of 1 over n, and all of these logarithms of 1 over 1 over n, they're just log n, so it's an average of log n, so it's just a log n. So the entropy of just n things selected, one of n things selected uniformly at random is log n. And that sort of fits with something we saw earlier, right? That log n was how many yes or no questions I had to ask you to find out which one of n things you were thinking of. So that's this connection to entropy, that's this connection to information, this connection to how many questions I have to ask you to find out what something is, the average number of questions I have to ask you. That's the first special case. The second special case is when n is 2. Now when n is 2, there are only 2 probabilities, right? But actually there's only one free choice. So we choose, this is like having a coin toss, right? So we toss a coin and there's a probability p that it comes up heads. So then there's a probability 1 minus p that it comes up tails. We plug these things into the formula for entropy and we get this thing that looks kind of gross. But it doesn't matter exactly what it looks like. What matters is the general behavior. So the first thing is, this thing is symmetric. So if I swap p and 1 minus p, then it's exactly the same thing. So flipping a coin that comes up heads with probability p has exactly the same amount of entropy as flipping a coin that comes up tails with probability p, because the outcome of flipping such a coin is equally surprising. Right? I'm not more surprised by one or the other on average. So this thing is symmetric. The other thing is when p is 0, or when p is 1, this is actually 0. But you have to be a bit careful, I guess, with like there's a division by 0 somewhere. But if you take limits in the right way, it's 0, and that makes sense because there's no information in a coin flip that comes up heads with probability 0. If you tell me you're about to flip a coin and it's going to come up heads with probability 0, I already know what you're going to get. It's going to be tails. So there's no information in a coin flip that comes up heads with probability 0. There's no entropy in that case. And then as you get closer to the middle, closer to a half, there's more and more entropy in this coin flip because I'm less and less able to predict what the outcome is going to be as the coin gets closer to fair. And then the absolute peak in the middle at a half takes the entropy all the way up to 1. And what that's saying is if you're flipping fair coins, I just straight up do have to ask you which way it came up, heads or tails, if I want to know what the result was. There's no way getting around it. It could be either, they're both equally likely. I just have to ask you. So a coin flip can only have 1 bit of entropy in it. But this also means that if I'm ever asking you a yes and no question based on some random choice you've made, like was your number bigger than 8? If you picked a random number, that's a random question. There can't be more than 1 bit of information, bits is how we're measuring these things, 1 bit of information in the answer to a yes and no question. So this gives us a different perspective on the guessing game we saw earlier. We said that the number of questions you have to ask to find out which one of some number of things you're thinking of is at least the logarithm of the number of things. And from an entropy point of view, that's because the second part of this is the entropy of a random thing. If you choose one uniformly at random, then there's so much information, there's this much information in telling me which one you selected. Whereas if I'm asking you yes or no questions, I can only get out at most 1 bit of information per question. So if I want to get all the information out, which I have to do if I want to work out which thing you were thinking of, I have to ask at least 1 question for each bit of information I'm trying to get. So number of questions, again, has to be at least the logarithm of the number of things. And in fact, we can strengthen this now. And there are a couple of reasons why it's worth bothering doing things this way at all, rather than just the counting we did the first time. And the first improvement is that really this logarithm of the number of things is not what's going on there. It's that that was the entropy of some random variable. And that means we can also apply this, that means we can now apply this guessing game type reasoning to cases where there isn't, where the options aren't all equally likely, like the lottery example. And the second reason this is interesting is that the reason we needed as many questions as there are bits of entropy in your choice is that I only get 1 bit out at a time, but I only get 1 bit out at a time if I'm asking questions where the answer is equally likely to be yes or no, where this probability of getting a yes is a half, so that the entropy of the question is actually 1 or very, very close to 1. So we also get the stronger result that if I want to get anywhere near this minimum number of questions, this log n questions, then the questions I have to ask you have to sort of split space in half every time. That's something we saw earlier. We didn't really give a reason for why that had to be true. And this makes this gives an explanation for why we need those equal splits at every stage. So that's a very, very brief introduction to entropy. But you could still reasonably say things like, well, why should I care about entropy? We've not done anything here that really we couldn't do by counting. And that is, again, that's fair. But I want to give you an analogy to something that you're maybe already convinced of the use of, which is probability. So probability begins as counting. The early applications of probability were people trying to work out gambling odds, like rolling dice, playing card games. And in all those situations, what you're really doing is just counting up how many of the outcomes, how many ways there are to roll a die, how many ways there are to draw some cards that result in you winning, how many ways there are that result in your opponent winning, and then working out which is bigger so that you know which side you want to be betting on. But the way probability is developed, we have lots and lots of tools for working with probabilities that are actually much, that allow us to do things much more efficiently than just by counting, and allow us to do things that are so complicated that really we perhaps couldn't practically do them by counting at all. So to give you one example that still really confuses me a little bit, it's far more powerful an idea than it really has any right to be. My research area is combinatorics, which means I study discrete objects of various kinds. And quite often, what we want to do is just show that some object exists. And quite often, it's difficult to show that something exists, because if you don't know where it is, you sort of don't know where to point at it. But quite often, you can show that if you build something completely at random, then there is a probability greater than 0 that the thing you build has the property you're looking for. And it's not wrong to say that, oh, well, if you want to show that something exists, you could just count them and show that the number of them is more than 0. That's not a particularly easy thing to do in many cases. Whereas showing that if you do something at random, you've got a positive probability of something working, that's much, much easier to get to grips with. And in the same way, there are lots of situations in which there are lots of tools for working with entropy, which I'm not going to go into, but they let you calculate things in a way that is much easier than counting by hand, even if you're in a situation where counting by hand would have been possible at all. Okay, so that's my brief advert for entropy. So now on to really the final part of this, which is why sort of the clickbaity part of the headline, which is COVID-19. So what's all this got to do with what's happening right now? Well, this is what I think it's got to do with what's happening right now. And it's to do with testing, right? So here we've got, suppose, I think this is 100 people, or it should be 100 people if I can count. At one point during making this picture, it wasn't 100 people, but it might be 100 people now. And we're going to imagine that 5% of them, say, have got coronavirus, right? So we want to test to find out which of these people have coronavirus. And the way everybody would think of doing that, and the way people are doing it all the way around the world, is what you do is that you give a test to each person, and you find out whether or not they are infected. We're going to pretend for this talk that tests are perfectly accurate. They're not, but in a world where they are perfectly accurate, one thing you're allowed to do is just test every person individually. Is that a good idea, though? Well, what is a test? A test is a yes or no question that you can ask about who is infected, right? So how many yes or no questions should we expect to have to ask to find out which people are infected in this situation? Well, for each person, there's just a 5% chance that they're infected, right? So the entropy of a coin that comes up heads 5% of the time is it's something, you work it out, you plug it into a calculator, and what comes out is 0.29 bits. That's how much information you need, on average, to find out whether a person is infected. We have 100 people altogether, so we multiply that by 100. So the bound coming from entropy is that, in principle, if we could ask the right 29 questions, we could find out which people were infected. Now, testing is not free, and 29 is less than 100. It's significantly less than 100. So if we could somehow actually get this, come up with some magical process that actually lets us work out who's infected using only 29 questions, that would save a lot of money. It would save capacity in labs. It would allow more people to be tested. Okay. So how can we do that? If we think right back to guess two, we had this silly picture, right? We wrote down all the possible sets of two numbers you might have been thinking of. So even if we simplify our current situation and just pretend that 5% out of 100 means exactly 5 people will be infected, it's more complicated than that. But if we assume that exactly 5 people out of 100 are infected, we could write down the list of all sets of 5 people out of the 100 and start asking yes and no questions about whether sort of the infected people are in the first half of the list or the second half of the list. But how are we going to get answers to questions like that? That's not a sensible question to ask a test to, it's not a sensible question that you can ask a testing center to answer. The kinds of questions a test center can answer is, does this sample I've got here have any coronavirus in it? So that's a big limitation on the kinds of question we're allowed to ask. But it doesn't mean there's nothing we can do. So here's an example. Here's 100 people again. What I could do is take these 100 people and split them into 10 groups of 10. Now, if I take the samples from these 10 people and in a group and mix them all together, that sounds weird, but you can do it, and then test the mixture, what I'll find out is there any coronavirus in the mixture? And what that tells me is whether or not anybody in the group of 10 was infected. Right? So in the case where there were 5 people infected, what we probably find is that in 5 of the groups, 5 of the tests come back completely clean. There's no coronavirus in them at all. And then 5 of the tests come back positive. So on the groups that came back positive, you might think we've not made very much progress because we did a test and we have no idea who was infected. That doesn't seem a very good return on investment. But on the groups that came back clean, we did a test and we found out from one test that 10 people weren't infected. And that's really efficient, right? Okay. So now, even if we just do the simplest thing you could think of and individually test every single person in each of these groups, that's a total of 10 for the first round plus 5 lots of 10 for the second round, so 60 tests in total. And that's brought the number of tests we need to find out who is infected down from 100 to 60. Right? It's not all the way to the magic 29, but it's a big improvement. It's saved a lot of tests already. But we were already being pretty stupid about what we did in the second round of testing, right? There's no reason I have to test everybody in one of these groups of 10. What could I do instead? Well, if there was only one person, if we knew there was only one person in this group who could be infected, then we'd like to do this maybe splitting in half trick again. And we don't know for sure there's only one person in this group infected, but we could try the splitting in half thing anyway. Right? So maybe we split a group in 2, and we're going to test, let's say we test the first half, so the 5 people on the left, and what we find out is that actually, no, that sample comes back clean, there's nobody in that group who has coronavirus. Then we switch our attention to the second half. We now know there's someone in here who's infected because there was someone in the whole group who was infected. We split into two. Again, we test the first half, and maybe this time the test comes back positive. One of these two people has got coronavirus. We don't know which, but one of them has. At least one of them has. So now we keep going, we split those in two, we test maybe the first person, and the first person's test comes back clean. But now, without doing any more testing, we know that the second person in that group was infected. So I did 3 tests there, and I found out that 1, 2, 3, 4, 5, 6 people were not infected, and 1 person was infected. So I've made a further improvement over testing these 10 people individually. And you can maybe start to see at this point that there's an enormous range of strategies you could follow for testing people. How many groups do I split people in in the first round? What do I do in another round? How many rounds do I want to have altogether? Is it better if for some reason I can run lots of tests in parallel? And these are all important questions. And mathematicians have been thinking about these for a long time. So here's, the last thing I'm going to flash up on the screen is a screenshot of a paper. So I just want to make a few remarks about what's on this screen. So the first thing is that this is an area called group testing. That's the older name for it. It's often now also being called pool testing. So if you want to know more about this, you can look up group testing or pool testing, and you might find what you're looking for. The second thing on this screen is that, well, okay, no, we'll say what this paper is about first. So that, yes, the second thing is the abstract is using a lot of fancy language, but this 0.95 is basically saying that you can get, by making the right choices, within 5% of this minimum value of 29 that we had. So in large examples, you can on average do about 5% worse than this minimum of 29. So that's a saving of about a factor of 3 in the number of tests that you have to do. The next thing is, this is a very old idea. So this began in World War II, where the US Army wanted to screen soldiers for syphilis, and the blood test for syphilis was very expensive for them to run. They had very low capacity. So they explored the idea of group testing to try and increase their capacity. The next thing is that you'll notice that there's a very recent date on this. So that's slightly misleading. This is an updated version of a paper posted to the archive. The first version went up in January 2019. And so this is still a really active area. Mathematicians are still working on this. And you might ask, like, what's with this 5% slack, right? Can we do better than that? Nobody knows. This is just the latest paper in a long line of contributions to trying to solve this problem. And also, you might notice it's a local contribution. It's not University of Manchester, but it's from Matthew Aldridge, who is a mathematician at the University of Leeds. They're not all that far away. There's important mathematical work going on close by. Now, there are various extra considerations. Interesting. There are various, that's probably this talk, and it's confused about the time. So I've talked about one very simple case where you do a test, you think about the next thing you want to do, you maybe do another test. That might not be a thing you want to do. Maybe you want to limit how many rounds of testing you do. Maybe which test you do in the future shouldn't depend on which test you're doing at the moment. Maybe there's some reason you can't actually mix together like 1,000 samples because you just lose the signal, but maybe you can mix together 50 or 100. And in fact, I think in practice, people have done 64. And that brings me really to where I want to close this, which is people often ask, like, why do people do maths? Like, what's the point? Especially research maths, right? Don't we know it all already? And the answer is, well, no, we don't. And also, we don't know always in advance what things are going to be useful. And what mathematicians are often able to do is solve problems before we need an answer, which is much quicker than waiting until we need an answer to solve the problem. Because once the situation comes along where we need the answer, we've already got it ready to go. And that is, and this is an explanation that I cling to, and also a lot of mathematicians cling to, I think, the idea that what we're doing might be useful at some point in the future. Be nice if it was. But for that explanation to make sense, when one of these situations comes along that mathematicians have a solution for, it would be nice if the solution was used. And group testing, pool testing has seen very, very limited use so far during the coronavirus pandemic. There's maybe a few 100,000 people worldwide who've been in systems that looked anything like this. And at a time when testing capacity is so strained and lack of availability of testing is meaning we're having to make huge changes to our lifestyles, I just don't understand why people aren't making use of the great work that mathematicians have already done. So thank you for listening, and I'll stop there.